Okay, so um, let me just make sure I am live. Um, okay. Hey, hi, Shub. Um, nice to have you here again. This is exciting. Okay, so today I'm going to do something new, which is binary search. So binary search is the next topic on my list. Um, it's an incredible algorithm, right? To search for items in an array. So, okay, so let's see. What do we do now? What do we do? So, binary search. Um, I'll link this in the description. I forgot to do that, so let me add it to uh the lectures. I mean the articles to read. I even left these other ones here, so let me edit that quickly. Binary search. Yes, so reading reading will be binary search like this, right? So save. Yeah, and I was going to link other resources, but I don't have light, and I needed to record quickly before I'm completely out of power. So let's read what binary search is. So binary search is an you know uh so there's iterative and recursive implementation, but we're just going to have a look at the iterative part. I've not done recursion yet. So yeah, so you can have a look at this. A binary search algorithm is a searching algorithm used in a sorted array by repeatedly dividing the search interval in half, right? So we have an array, right? And we want to search for an item in it. Now, for you to implement binary search, the array has to be sorted. It has to be a sorted array, and for you to use a binary search algorithm on the array to look for an item, right? So, yeah, the idea of binary search is to use the information that the array is sorted, right? And reduce the time complexity to O log n. Okay, cool. So we have an image here. What is binary search? Binary search is an algorithm. Binary search algorithm. Okay, it's a search algorithm used to find the position of a target value within a sorted array. It works by repeatedly dividing the search interval in half until the target value is found or the interval is empty. The search interval is halved by comparing the target element with the middle value of the search space. So I think, you know, so let's see what that means. So I'll use an array. Which array should I use? Let's say we are looking for. Oh, this is what I did yesterday, so I'll delete this. Um, I want to use a proper nice array, so I'll use this one. Is this sorted? Yes, it is. Let me just use my own array. So I'll just put um, you know, I'll create array. I'll say this is nums or I'll call this capital N, is equal to an array like this. I'll say 1, 2, 3. Okay, let me start from 2. So 2, 4, I can put 6, 8, 10, 15, right? Let me just do it like this. So let's say this array has been given to us, and we have a target t equal to 8, right? So we want to look for 8 in this array. Now, one way we can do this is to start iterating through the array until we meet our target, right? But this way of doing things is actually O of n time, which is not really fast compared to a binary search, which is, O log n, right? So instead of using O of n, you can see the binary search is in O log n time complexity, which is faster than O of n, right? O of n simply means we have to go through each item in the array until we meet our target. But O log n says we can start by choosing an interval. Usually we'll start from the beginning, right? We'll have a left and right pointer. Now our interval is within this window here, right? So we need to check if the target we are looking for is within this interval. And one way to do that, let's say we are giving, let me give you an example before we even come to this. Let's say we are giving a range of numbers from 1 to 100, right? And we are told to, choose a target or guess a number, right? One way we could do that is to choose 50, right? When we choose 50, which is the middle of this interval here, we will then be told whether this interval or whether our number is bigger than the target or not. Now this gives us a very big advantage because now we know we don't have to guess even when the number is 2, right? Even when the number is 2, we know we will not guess will not keep guessing numbers between. Wait, sorry, let me just go back again. So here's what I meant to say. Let's say we are playing a game, right? And we're asked to guess a number. So let's say the computer chose a number, or we have a secret number here, right? Set to something, right? We don't know what the secret number is yet. And the game is such that when we guess the secret number, right? If our guess is smaller than the secret number, we'll be told, to try again, right? Because our guess is small. Or if it is bigger than the secret number, we'll also be told to try again. But this way of selecting, so our guess is supposed to be 50, right? We can choose 50 as our guess, and by choosing 50, it gives us an advantage that, okay, we have 50 more items on the left, or 49 more items, right? And another 49 more items, and we are in the middle, right? So this way we'll know, okay, do we will we search the remaining 49 item if our guess is smaller than 50, or we'll search the remaining 50 item if our guess is smaller than 100, right? So if the secret number was let's say 10, right, and we chose 50, we'll be told, okay, our guess is actually higher than the secret number, so we'll know where to search in. So we'll search between this interval from 1 all the way to 50, right? So we'll take half of this again. This will be 25, and then we'll be told again our guess is smaller than the secret, and then we'll go back again and look between these two, right? We'll divide this 25 by 2 again. When we divide 25 by 2, this is not divisible by 2, but let's say we get to let's say 14, right? Sorry, let's choose 12, right? So when we choose 12, we'll be told again our guess is smaller or bigger than the guess, right? bigger than the secret. So since our secret is still 10 and our guess is 12, we'll go half again. So we'll keep dividing by half, right, until we get to the point where our guess is now equal to the secret. So the same thing happens here, right? When we are looking for an item in an array using a binary search, we'll keep dividing each time. We'll try to get the middle point, right, of the array every time we search for an item. So to get the middle, we then start from these two ends, right? We'll do the sum of these two and divide it by 2, right? So this would have been 0. The length of this array is what? 1, 2, 3, 4, 5, 6. So this is 6 minus 1. This is 5. When we add these two and divide by 2, right? So we'll also round this up. We'll get 2. So what is 2 here? 2 will be at this position here, right? We know our midpoint, right? This is going to be our midpoint. I'll put mid. This midpoint here, right, is still less than our target. The value at this midpoint is still less than our target. So what do we do again? We'll just move this left pointer towards where we were before. So we'll just move this here. We'll move the left pointer now, right? We'll move it here. Anytime we have the target being bigger than our current midpoint, we always need to increase the value of our left pointer, right? So we need to increase the value of our left pointer so that we can search within this window. Sorry, hold on, what did I just say? When the value of the target is bigger, right? When the value of the target is bigger than our current middle, okay, so we reduce our right pointer to this point here. Hold on, I think I'm confusing myself. Hold on, let me really erase this first. So it's a binary search, and a binary search is such that we repeatedly divide our array into half, right? We get half portion of the array and then we search within that part, right? So when we take half of this array here, it will be at this position. Let's say our target is 8, right? And at this point, when we divide this by 2, right, when we try to get our target is here, this is our target, and we want to divide this array into half and search within a favorable half, right? A favorable half is just a half where our current targets could possibly be in, right? So let's say now when we divide this into 2, the length of our array, or we do left plus right, right? The left is going to be equal to 0. The right is going to be the last item in the array, which is the length of the array minus 1. This is going to be 0, 1, 2, 3, 4, 5, right? So when we find half of these two values here, so we add the left to the right, divide by 2, and we round it up. So this will give us 2.5, but because we are dividing this way, this will be equal to 2. Now the 2, right, represent our midpoint. So our midpoint is going to be here. So where is 2? So this is 2 here, right? This is 2 here, which means this value here is less than our target. When the value is less than our target, we move our left pointer towards that point, right? We move our left pointer towards this point here, and then we will search within this window. So this is the window in which we'll perform our next search, right? And we'll keep doing this. We'll keep shrinking the array in each iteration until we get to a point where the left and right pointers, right, until we get to a point where the middle or the midpoint that we always calculate, right, is pointing to the value of our target, or the midpoint is equal to the index at which our target appears, right? In this case, this will be 0, 1, 2. This will be 3, right? So that is how we perform a binary search. And a better way to even demonstrate this is in code. So I'll write a code to do that. So let me show you what I meant by that. So let me say I'll call this define. I'll say bin search, right? Bin search, and bin search is going to be, you take an array. I'll call this nums, and nums is going to be, and the next thing to take is the target, right? So our target, and then what we need to do now is to iterate, right? But before we don't iterate based on the items in the array, because that will give us O of n time complexity. We want to iterate within a portion, right? Within the left and right borders, or the window where the left and right appear as the borders of that particular window. So here's what we need to do. First of all, we need to choose our left and right. So our left will normally start from the start, right? I'll put this like this: left, right, left and right. Our left will be equal to 0, and our right will be the last item in the array. So it's simply the length of the array, the length of nums minus 1, right? So this is how we initiate our left and right, and our iteration has to continue until the left and right pointers are, overlap and pass each other. So let me show you what I meant by that. So let's say we kept looking within this array. So let's say 1, 2, 3, 4, right? Always a sorted array. We start the left pointer here and the right pointer at this point, right? So when we keep searching, right, let's say the value we get, the midpoint between this left and right is always less than the target, right? Let's say our target t is equal to 5. Now 5 is not in this array, so what we need to do is we need to keep moving this towards the right, the left pointer towards the right, until it gets to a point where the left pointer now is no longer the same as the right pointer and passes it, right? Or it overlaps. So when that happens, we know our iteration needs to stop and we don't need to continue iterating again. Otherwise, if we have the left and right pointer at a particular position, let's say my the target here is equal to 3, right? When the target is equal to 3, at this point we know the left, when we look for the middle, right, the middle will simply be this value here is simply be 2. This will be easy to return. Let's say we have 5 and we are looking for 3 in this array, right? So our right pointer will start at this point at the end of the array, and the left pointer will start here. So when we look for the midpoint here is going to be equal to 2. Is going to be equal to 2 here, right? This is our midpoint. Now the value at this midpoint is 3. Is 3 superior or equal is 3 superior to 5 or less than 5? 3 is actually less than 5, so we need to move our right pointer up, right? We need to move this towards this point here. But since we don't really need to move it here, but we need to move it one past that position, because we've already seen this before, right? Then we find the midpoint between these two. The midpoint between these two will certainly be so this will be at position 3 plus 4, right? This is 0, 1, 2, 3. This is going to be 7. 7 divided by 2. This is going to be 3.5, right? 3.5, and we round it up. This is going to be 3. So what item is at position 3? So this is going to be 0, 1, 2, 3, right? So since it's still equal, right, we need to, we'll end up here with that calculation, right? We'll be at this point, so we need to move the left pointer again, right? So there's no problem when the left and right pointer are at the same position. This is just fine, right? So we calculate again until we get to this point, right? We get to this point and we get this 5 here. Now this might seem like it is better to use a lookup, right? Looking at each value in the array, but when you imagine how large the array will be and the value could be at any point in that array, this method of doing things is actually the best, right? And the time complexity of this is O log log n, right? So let me go ahead and show you this in action. So I'll bring back this. I'll bring back this method, right? So I'll say okay, sorry. So here's our array. We start from the end and the right. So our loop is always going to be a while loop while the the left is less or equal to the right, right? While that is, then we want to do something. We want to say, we want to say if, so we first of all need to calculate the midpoint, right? So I'll say midpoint, I'll call this mid is equal to, the mid is going to be equal to the norms at, sorry, it's going to be equal to the left plus the right, left plus right, divided by 2. This double division just rounds it up to the nearest 0 value, right? So instead of us to get a decimal place, we get a whole value, right? Yeah, so now we'll need to verify if this midpoint is actually the value we are looking for or not. So let's say we'll now put some condition here. Say if the norms at the midpoint, right, norms at midpoint is superior to our target, right, is superior to our target, then we need to reduce the right pointer, right? Because we know this the array is sorted from smaller value to big larger values. So if we find a value where the midpoint is now a value in the array where the midpoint, right, the midpoint points to is now superior to the target, right? Since we know the array is sorted in increasing order, we know we are at a larger portion of the array, so we need to reduce our right pointer towards the lower part, right? So we'll say so our left is simply going to be equal to the midpoint, right, minus 1, right? Else if the norms at the midpoint is less than the target, right, is less than the target, then the right should be equal to, sorry, is the right here and not the left. So right, my bad, right is there, left should now increase, right? Left should be equal to so left should be equal to the midpoint plus 1, right? Else, right, or else it means the midpoint is at the position is at the index of the target, right? Or the value at this midpoint is equal to the target. So we return what do we return here? Since we are looking for the value, right, let's return the midpoint instead. We return the midpoint So I'll just do this. I'll say, you know, since we are returning something, right? Okay, when we don't see anything, I'll just return -1. So which means negative index, right? Solution. I'm so used to doing this, so I'll just say bin search nums. So what kind of numbers should I use? I'll use my example here, right, which is 2 4 6 8, and I said 8 is at position 3, so our value should be 3 instead. So 2 4 6 8 10 15. So I'll say nums is equal to 2 4 6 8 10 15, right? And the target here, the target we are looking for, okay, since I'll be changing the target, so I'll just pass it directly. So the target, the nums, will pass in nums, and then our target should just be 8, right? So our expected value should be 3, right? So let's say print solution, right? So I'll do that, print solution, and run this. Now you can see our value is 3, right? So this is how we will implement a binary search going forward. Just continuing to have the array, which will be the portion in which we are searching for our targets every time we iterate through the array. It's getting dark. So we need to have the array every time, right? And there is a question on that in LEETCODE. So I'll come here. And it says, given an array of integers nums, which is sorted in ascending order, and an integer target, write a function to search the target in the nums. If the target exists, then return its index. Otherwise, return -1 if the target does not exist. So here is our, some test cases here. So let's quickly implement that. So I'll write all the code here since it's not so much. So we'll have a left. You know what? I've already written it here, so there's no point repeating it again. So I'll just copy this and run it here. So we need to push this inside. Okay. Yeah. So here's the implementation. So when we see the target, right, we return the target index, which is this midpoint here. Otherwise, we return -1 when it's not seen, right? So yeah, you can see the solution worked. I'm not sure. So it is not the best of solution. In terms of time complexity, it's still kind of below average, but this solution actually works. Yeah, I mean it works, but let's say we're trying to look for an item in an array, right? And we know the array is sorted, right? If the array is sorted, oh, they've brought back the light. If the array is sorted, then if the array is sorted, right? If the array is sorted, which is 1 2 3 4, right? This is sorted array. I'll call this n, right? And our target here is 8. Now we know to implement our binary search, we always take the right the beginning and left, right, as our left and right pointers. So I'll put the left and right pointers here. Now, if the target is not, within this interval, right, or if the target is bigger or smaller than um our our left pointer or right pointer. So if it's bigger than the position where the right pointer is, then we know our target is not going to be anywhere within this window here. Same thing for the left pointer, right? If we know that our target is, say, let's say -1, and our array started from 1, right, we know our targets would definitely not exist, anywhere in between. So for us to even make this more efficient is to check first, right, if the target is within these two borders, right. If it is, then we will say, okay, fine, we can then look in between this. Otherwise, we just return -1, as in we didn't find that value. So let me put a case here, right. I'll say if um if if the left, how do I do this? So if item at the left, so nums at left, right, is less than the target, and so I'll not put and I'll just put this comparison operator here, and the target is also sorry, it's not, let's put it like this. If it's less, if the target, okay, sorry, this is the only case where this will happen. So let me say, if this, I want to put this like this, right? So if nums on the left is bigger than the target, or the target is, larger than, let me do it this way. So less or equal to the target, right? And target should be, equal to nums at right. So only when the target appears within this window, then we can, run this loop. Otherwise, we return -1, right? So I'll just say only in this case, else we return -1, right? So let's see. So this will only prevent us from, okay, something is wrong. Oh, okay, so invalid syntax here. Okay, so if the target is less or equal to, no, the target has to be superior to or equal, right? If the target is superior or equal to the nums, what am I doing? We want the target to appear within this interval, right? So this is already wrong. So I'll say nums at left, the target should be less than it, right? And the target should be, less or, something like this. The target can be larger than the number at left or equal to it, or the target can be, yes. So this should work. This should work. And let's submit this and see. Hopefully this improves the solution a bit better. Well, in terms of memory, it did, but like the time complexity is still not much different from what it was earlier. Let's see, is there the constraints here? All the items are unique. You must write an O log. Yeah, this is it. So am I doing anything extra? Anyways, this is the solution. I'll just take this here, right? I'll just copy this and put it as my solution here. Okay, let me copy everything. Right, so here we copy everything here and paste it here like this. So I'll say solution here. Okay, so so we import list, right? And I'll just take this here, say git add git commit dash I'll say binary search, sorry, binary dash search. Hold on, where did I create this? It's in the playground. So sorry, I need to put this on an actual file. So this is LEETCODE 704, a new folder coming in now. So I'll put this new directory binary search, and I'll say this is file lit dash, I think 407, right? 704, and I'll set this to binary search. So I'll put this here and save and just open my terminal. So I'll say this commit dash m, sorry, not capital M, binary, oh sorry, lit 704 bin search, right? Bin search, yeah. So git push. Okay, before I push, I need to solve one more question. So we have a second one, which is a medium question, but this time around, this question is actually similar to what we just solved now, right? But this time around, it's just the same simple binary question, but with arrays, arranged in a form of matrix. So, or with matrix, right? With matrix. So let's read the question. You are given an integer. You are given an m by n integer matrix with the following two properties. Each row is sorted in non-decreasing order. The first integer of the row is greater than the last integer, right, of the previous row. The first integer of each row is greater than the last integer of the previous row, right? You can see this here. So given an integer target, return true if target is in matrix or false otherwise, right? If the target appears anywhere here, right, whether it's in this first row, this second column, but in this case it was in the first row and the first column, a second column, right? So you must write a solution in O log m times n, right? M is I think m is the row and n is the column. Now I'm not going to write an O log m times n time complexity solution. I'm just going to implement a brute force solution and look at how to improve that later on. So let's start with this, right? So we are given a grid, right? Or in other words, and let me delete this. We are given this table here, right? And we are told to search the table and look for a target, right? Ransom is in the channel. How are you doing? Yes, I'm good. How are you too? So, let's see what goes on here. So we are given this grid, right? This matrix. Now, one thing to always do is to visualize this as an array within an array, right? This here, right, is one array. Let me here. This portion here is one array, right? This portion here is one array. This is a second array, right? So the rows are literally, arrays of the matrix, right? The matrix, even though it's a grid that has columns and rows, right? The rows are simply, you know, the arrays that are part of the matrix, right? So now, when we dissect this into, rows, right? Rows or arrays that are within this matrix, we'll be left with the simple binary search problem for each one of these rows, right? We'll be left with a simple binary problem for each one of these rows here. So now here's what we need to do. We will iterate each row, right, and perform a simple binary search on the row, right? If the value is not within this row, right, if the value is not within this row, we'll move to the next row, right? And if the value is not here, we'll move to the second row. But another thing to note is when we are searching within each row, we also need to take in account the left and right pointers, right? And check if our current target is within this margin or within this window here. If it's not, we know it can't possibly be anywhere else but, in the next row, right? So we simply need to, exit that first iteration and come to this point where we can look within this window and find, where that particular target is, right, within this row, right? So we can find it anywhere here. So let's say our target is 3, right? 3 will be found in the first window, right, in the first row. But let's say our target is 34 now, right? When we look at 3 and when we look at the first row, we know each row, right, each following row has values that are larger than the previous, right? So if our target is not at the left or right pointer, we know it will possibly be in the second row. And if that row also doesn't satisfy that solution, we move to the next, and then only then we begin to look at each item. But we don't look at each item, we divide the entire array by 2 and look at each half. If it's not in this half, then we'll look at the second half as well. So that is how we'll solve this problem. And the time complexity is not really going to be O log m times n. I'm just implementing a brute force solution and see how it will work. So let's go ahead and do it that way. So I'll take this, right? So we have a binary search question and it is number 74, 2D matrix. So I search 2D matrix. So I'll come here and create my array. So my array is going to be, my file name is going to be leet 2D, leet 74, right? 74, and it's going to be equal to, the name is going to be search 2D matrix. So I'll say 74 dot search 2D matrix, like this, right? So then I can take this. So first of all, we want to iterate each item in the matrix, right? or in other words, we want to iterate each row and then implement the simple binary search solution on each row. So here's what we need to do. I'll say for I, again, this is not the best solution. I'm just using a brute force solution to see how this will work. So I for range in length of the matrix, right? Now I is simply going to return the index. So I'll call this the current row, right? So current row will be item at this. So matrix I, right? So that's going to be the first one, and we'll then look for the left and right pointers, right? So the left is going to be equal to 0, and the right is going to be equal to the length of the array. So 0 and length of the current row, right? Current row minus 1, right? So here's what we need to do next. So we'll take left and right, and what else we need to do? What else? Left, right. So we first of all check if the current if our target is within this window. So I'll say current row, right, left, and if it's within this window, right, I'll say targets, right, targets, and current window at index of the right pointer, right. Then we can begin to perform our binary search. So we'll say while left is while left is less or equal to right, while left is less or equal to right, we want to find the midpoint. So we'll say let's just call this mid, right. Mid is simply going to be equal to the left plus right divided by 2 and rounded up. And we'll say if item at left, right, so if the midpoint current window midpoint is superior to the target, then we reduce the right pointer, right. So right should be equal to the midpoint minus 1. Else if the current row at the midpoint is less than the target, right, is less than the target, then we want to do this. Left is equal to the midpoint, right, plus 1. So we want to increment it by 1. Otherwise, we found the midpoint, and what do we do here? I'll just see, what are we returning? We're returning true. Okay, so we say else return true. Otherwise, what do we return? True or false, right? True or false. Okay, so if we don't return true, now there's one thing I missed here. If this is not, the target is not within this interval, we simply need to skip this iteration and move to the next item or the next row, right? So else continue. I'll just put continue here, and yeah, so that's about it. Until we are done with the iterations, I'll just return false like this. So here we go. So let's copy this and run this first and see what we have. Okay, so let's see. Continue. Um, and say this, that. Let's run this and see. This will not be, the most effective solution in terms of space. I mean, time complexity, right? Although we are not creating any more memory in space, I'm sure you know there is room for improvement anyway. So, uh, what? Okay, this works in terms of um time complexity. This is good, but space complex. Oh god, this is horrible. 7.11%. That's not good at all. So, which is why we're asked to use this. Uh, I don't know if this is working right. If this is O log n, even though this not, yeah, this is still O of n complexity, right? Because within it we still have O log n, right? The normal binary search is 0 O log n, right? But when we are iterating like this, right? When we are iterating, this is O of n. O of n. This here is O of n time complexity. But because we have this condition here, we are jumping straight to the point where we find um we find an array that will possibly contain our target, right? So, I don't know. I think I need to go back and and see what exactly this is about, right? So, anyway, for now, that's enough for the first time learning about binary search. So I'll just do git add git commits dash m. I'll say this is bin search. Sorry, bins, or let's say leet code. That's, I think, is 74, and I'll say bin search like this. Okay, hold on. Oh, commit as double T. Okay, so git push origin main, like that. Okay, so for now this is okay. um I'll continue learning more about binary search and solve more LeetCode questions and come back with better explanation of this topic. All right. Okay, so there's a chat in it. So I was really doing why you're doing it. Yes, that's the point. That's the point. Always show up. At least solve one question in a day. Uh, it will go a long way, after a while. All right. Take care, everybody. And today's there's not been light, and I will see you